Is basically just another way of saying the square root. All right. So when we talk about simplifying radicals, what's our goal here? Well, we're going to try and have some kind of number inside that radical or that square root. We're going to try to make it as small as we possibly can. Simplifying it, right? So our goal here is to find the factors. What's a factor of a number? What are the factors of 50? 5 times 10. So factors of a number are what? Two numbers that can be multiplied together. Okay? So I want to find the factors that are perfect squares. No problem. What is a perfect square? Okay, so perfect squares, when you take the square root of a perfect square, what kind of answer do you get? A whole number, or the same number, right? So here's the question, can I take the square root of any number? Yeah, I really can, but if I take the square root of like 7, my answer is going to be a what? A decimal. So we're looking for perfect squares, the ones that come out exactly right. All right? So in 50, what's a perfect square that's in 50? What? Somebody earlier said 5 times 10, right? Well, are either 5 or 10 a perfect square? No. So those are factors of 50, but we want one that's a perfect square. So think about other factors that would be a perfect square of 50. 25 times 2. So in a sense, what we're doing here to simplify this is to break it down where one of the factors is a perfect square. And preferably, we would want that perfect square to be the biggest one that we possibly can. Meaning, in this case, 25. Okay? There isn't another one for this, but when we look at another example, we'll show that to you. So then we come back and we ask ourselves, can I take the square root of either of those numbers? Can I take the square root of 2? Again, yes, I can, but I'm only looking for perfect squares. So if I can't take the square root of it and get a whole number, I'm just going to leave it on the inside. If I can take the square root of it, though, that answer is going to go to the outside. So what's the square root of 25? So in this case right here, my 5 goes to the outside. I can't take the square root of 2, so I leave it on the inside. And so I simplify the square root of 50 into 5 square root of 2. Now, is it really simpler? It's just easier to use, I guess. All right? So let's try it out. The square root of 80. Now, in this case, you might not be able to see the exact perfect square or the biggest one, so you might have to do this multiple times. And that's okay, too, because if most of us looked at 80, our first thought would be what for a perfect square? 4, right? But if I did 4, I'd have 4 times 20, and 20 can get broken down again. So we'll do it that way for this time, just so you can see that sometimes you might have to do it multiple times. So I'd have 4 times 20, and then again I ask myself, what's the square root of 4? If I can do it, that answer goes to the outside. So I would have 2, and then the square root of 20. Now 20 isn't a perfect square, but I have to stop and think for a second. Can I take the factors of 20 and get another perfect square? What are the factors of 20 that would have a perfect square? 10 and 2 are either one of those perfect squares. So those are factors again, but we want a perfect square. So what's a perfect square factor? Yeah, 4 times 5, right? So instead of 20, we have 4 times 5. What's the square root of 4? When I get an answer, where does it go? To the outside, but there's already something there. So what do I do with those two things? I multiply. Okay? So this 4 is going to bring another 2 out here. I'm going to multiply those together. 2 times 2 is 4. And then, can I take the square root of 5? No. So I leave it, and I get my answer. 4 square root of 5. Okay? Let's try another one. I gotta think though. Let's do the square root of 90. Try it out. See what you get. So again, I'm thinking of perfect square factors. So again, if I don't know factors in the first place, what do I have to do? I got to get my calculator out, and I just got to start taking 90 divided by whatever those numbers are. So again, think about perfect squares. Let's start this way right here. What are the perfect squares? Ryan started a little bit ago. 1, 4, what else?
16.
Missed one. 9, 16, 25, 36, 49, 64, 81. What's 10? 100, 11, 121, 12, 144, 13, 169, 14, 196, 15, 225. You should definitely know through 15. Okay? All right, so try it with 90 now. Find a perfect square in 90 and then break it down. How to do? What is my perfect square in 90? 9 times 10, right? Square root of 9? Where does that answer go? On the outside. Can I take the square root of 10? Evenly or whole number? No. So I just leave 10. Can't break 10 down into anything. Well, I can again, 2 times 5, but neither one of those are perfect squares either. Okay? Any questions there? So now we try the same concept when we talk about expressions. If I use that word expression again, what's that mean? We talked about this the other day. What was an expression in math? It's a problem that doesn't have what? An equal sign, okay? So when you talk about radical expressions, you're talking about problems that include variables. All right? So if we do radical expressions, these are just problems that include variables. We are going to do the numbers or the coefficients. The same as we just got done doing with the last 3 examples. So whatever number's in there, we just try to break it down. With the variables, though, you're going to take this. Now, why do we call this a square root? Why do I call this right here? Why do I know that this is the square root of 90? Any idea? So, if I told you, for instance, that this was a variable of x, what's the exponent on that? 1, right? Do I ever write that 1? No, but I can, right? all the time. What's the coefficient in front of that x? 1. And do I ever write that? No, but it's always there, right? And you can, okay? So why is this the square root? Because there's actually a little 2 right there. I call it the armpit. The armpit of the radical. There's a little 2. That's why it's called the square root. Because I could actually have the cube root of it, or the 6th root of it, and then the little number in the armpit changes to that number. But that's why this is the square root. We just don't ever write that 2. Just like we don't write these 1s. That make sense? Okay, so when we're going to do this now, radical expressions, and there's variables in it, we're going to take each exponent and divide by 2. And I'm going to do this as much as I possibly can, and however many that I can do that to, it's going to go to the outside. So, for instance, if I have a variable that has an odd exponent, I can't get all of them out, right? There'd be 1 left over. That's the only time you're going to have a variable left in the inside in these problems. So, for instance, it's probably easier if we have an example. 18, a to the 5th, b to the 4th, and c to the 7th. So again, I'm going to do the exact same thing that I did with the numbers before. What's a perfect square in 18? 9 times 2. So square root of 9 goes where? Outside. To the outside, right? 2, I can't do anything with, or at least a perfect square, so I'm going to put it on the inside. Now I'm going to go through at each variable, and I'm going to look at its exponent and divide by 2. So can I take 5 and divide it by 2? But can I take 2 out of 5? Yeah. How many times can I take 2 out of 5? 2 times, right? So basically, I'm going to break this a to the 5th down into a to the 4th times a. Would you agree with that? Because 4 plus 1 would get me back to my 5. Okay, so a to the 4th, if I take 4 divided by 2, how many times did you say that was? 2. Just like when I did my 9, when I take the square root of it, my answer went to the outside. The same thing happens with my variables. So my a turns into 4 goes into a 2. And then because the original problem was an odd number, I'm going to have 1 that's left over on the inside. Whenever you have 1 left over on the inside, it cannot have an exponent greater than 1. Because if you had 2 here, you could take another one out. If you had 3 here, you could still take another one out. So the only exponent on your variables on the inside or underneath your radical is going to be a 1. All right? So same concept. What do I get for my b's? B to the 4th turns into what? B squared, and where's it go? To the outside, because again, I did it. Just didn't leave enough room. So 3a squared. How many b's go to the outside? 4 divided by 2, right? So b squared. And now what do you think about the c's? I'm going to break c to the 7th into what? C to the 6th times c to the 1st. So 6 divided by 2 gets me how many c's on the outside? C cubed on the outside. And where's my c to the 1 staying? On the inside. Now, when you look in the back of the book for your answers, the book will put absolute values around this. Don't worry about the absolute value parts. Okay? For right now, that's kind of above our thinking. But this would be my answer. So, same concept, it's just a little different with variables. Alright, let's try one so you can try it on your own. The square root of 12 x to the 5th y squared. Try it out on your own. Again, do the numbers exactly like what we did before, and then we're going to do the variables separately. So again, with the numbers, I'm looking for perfect squares. If I can take this perfect square, it's going to go to the outside. Move everything else to the inside. So I get 2x squared y times the square root of 3x. Right? Everybody agree? 4 times 3, what are my numbers? Square root of 4 is 2. My 3 stays on the inside. X to the 5th gets broken down to 4 times 1, which is 4 plus 1, really, in exponents. So that's my 5. X to the 4th, 4 divided by 2 gives me x squared. My 1 left over. Again, odd number exponent. There's got to be 1 left over on the inside.
So what if I had 3x2y to the times the square of 2x? Because I did 6 and 2 for my numbers.
But a 6 is perfect square.
Oh.
Okay? So your 6 and 2 are factors of it. You just got to have a perfect square factor every single time. Make sense? All right? Questions with these kind? So then the next thing they talk about is multiplication. Did you guys get to this section even last year? No. So you haven't done any of this stuff yet? All right. So now we're going to talk about radicals with multiplication. So if we would have, or if I would have taught you this when I was doing algebra, I would focus in on this. You're going to multiply the outsides by the outsides and the insides by the insides. Now what I'm talking about here is the numbers with respect to the radical sign. So the numbers that are on the outside of the radical and the numbers that are on the inside of the radical. I can never multiply across the radical bar. Okay? So it's always the outsides by the outsides and the insides by the insides. So what that means is this. If I have 4 square root of 5 times 3 square root of 8, I'm only concentrating on multiplying the outsides by the outsides and the insides by the insides. And then, of course, I got to simplify at the end, but I'm still focusing in on that. So on my outsides, I guess you can think about them as coefficients, but they're not really considered coefficients when we're talking about radicals. But I'm going to do 4 times 3. Okay? So I get 12. And then on the insides, I would get what? 40. All right? Now, a lot of times when you start going fast in your homework or in the quiz or whatever, you're like, well, I solved the problem, I should be done. But you also then have to stop and go back and see if I can simplify the radical like we did at the very beginning. So you got to ask yourself, is there a perfect square in 40? What's my perfect square? 4 times 10. Exactly right. So now that's underneath my radical. What's the square root of 4? 2. When I get an answer, it goes where? to the outside, but what do I have to do with my 12? So this turns into times 2. So 12 times 2 is 24, and what's left on the inside? Square root of 10. I can break 10 down into 2 times 5. Do I want to do that?
No.
Because what? It's not a perfect square. Exactly right. Make sense? Okay, so the square root of 36 times the square root of 81. So we're thinking about what we just introduced, outsides by outsides and inside by insides. How many people really want to do 81 times 36, especially if I don't have a calculator? Probably not, right? So let's simplify, or try to simplify first. Can I take the square root of 36? Yeah, what?
6.
Square root of 81? 6 times 9? And I get my answer there. So don't, just because you're told to do something, always look to try to make it simpler at the beginning. Alright? Let's try another one of this. Let's say 3 square root of 7 times 10 square root of 4. Try it out. See what you get. 3 square root of 7 times 10 square root of 4. Everybody get an answer? So I'm going to say 30 times square root of 28, right? Outsides by outsides, insides by insides. Then I'm going to take a look at 28. Well, I can break 28 into 4 times 7. What's the square root of 4? 2 times 30? We should have gotten 60 square root of 7. How do we do? Okay, make sense?
Yeah.
All right. So if we can multiply them, then we can divide them. All right. So when we divide radicals, there's a couple of funky rules with this. This is where we might have to take a little bit more time if you haven't done this before. When I divide radicals, okay, the first example, if they wrote the problem like this, the square root of 49 divided by the square root of 36, this is equivalent to one giant radical and saying 49 divided by 36. Just two different ways of writing the problem. Okay? So, if it's written like this, you can rewrite it like this or vice versa. But the first thing that I'm going to do is try to simplify the top and bottom without actually doing division. Okay, so this could be, can I take the square root of those numbers? Can I divide those numbers? Whatever it is that I can make it smaller. So on this one, it's probably better for them to write it this way because I'm breaking them up into their own radical, and then maybe I can tell or see that each of those are what? Perfect squares, right? So I'm just going to simplify. What's the square root of 49? 7. What's the square root of 36? 6, and I'm done. That's it. So I'm trying to make it as simple as I possibly can. Sometimes these two numbers will be able to be divided by. So if I have, if I have the square root of 56 over the square root of 4. So now, is 56 a perfect square? No, but the square root of 4 would be a perfect square, right? But before I do the square root of 4, maybe I look at the two numbers and I rewrite the problem with one giant one like we did up here. And can I take 56 divided by 4? What's 56 divided by 4? 14, right? So now, if I divide underneath there, I'm going to leave it underneath the radical. So basically now, I just did division, but I left it underneath the radical. So what's 56 divided by 4? That's my 14. Can I take the square root of 14? No. Can I break 14 down into a perfect square? No. So again, I'm done with that. Okay? Those would be the two like basic ones. Now we get into the funky rule. 3 over the square root of 5. So the biggest thing that you have to know with division is a big star here. You can't have a radical, square root, however you want to think about it, in the denominator of your answer. So this problem, I can't really do anything anyway. Again, just like what we talked about over here, the outsides times the outsides and the insides times the insides, I can never take, if this was a 10, I cannot take 10 divided by the square root of 5 and reduce it. Because one's on the outside and one's on the inside. So I can never go over that. That radical is kind of like a barrier. I can't get through it. All right? But I also don't want to leave this radical 5 in the bottom. I can't have it in my answer. If you would leave this as your answer, this is wrong because you didn't simplify it. Okay, so in order to fix this, you're going to multiply by 1 in a sense. And remember, how can I make 1? Well, I can make 1 by taking anything and putting it over itself. Right? 3 over 3 is 1. 7 over 7 is 1. Radicals are the same way. Okay? So I'm going to multiply by 1 by taking the radical and make a fraction with itself. But remember, this is the key here. I'm going to multiply. So I'm going to come back up here, I'm going to multiply, and I'm going to put the radical over itself. Whatever's in the denominator, I'm going to multiply it by a fraction of itself. Now, if you thought about multiplying by fractions way back when, what's the first thing that they tell you to do when you're going to multiply by fractions? Look diagonally and do what? Reduce or simplify. Well, if I simplify this, what happens? My 5's right here would cancel out, right? But what would be left over? 3 over the square root of 5, and I'm right back to my original problem. So this is the only time that you never want to think about simplifying when you're dealing with fractions. All right? So we're going to do this. We took our radical. Now, multiply straight across. Again now, we got to go back to our rule over here. Outsides by outsides, insides by insides. So again, I'm going to come back here and I'm going to multiply straight across the top and the bottom. So on the top, I'd be left with what? Outsides by outsides, insides by insides. 3 Square root of 5, right? I can't do anything because one's on the outside and one's on the inside. Now I'm going to do the bottom. What's the square root of 5 times the square root of 5? What's 5 times 5? 25, right? But that would be underneath the radical. Okay? Now, can I simplify this? 3 square root of 5 stays the same on the top. What's the square root of 25? 5. So notice what happened when I took a radical times itself. A radical times itself ends up being what? Just the number, but without the radical. This is true every single time. Did you know about that? Or is that something that you've never seen before? Probably not if you didn't get to this part. So again, big star. Any radical times itself is the number or term under the radical. Now, if you forget this, you can just do the multiplication and it'll always end up being that way. But it does not matter what that number is. The square root of 63 times the square root of 63 is 63. I'm not going to go through the process of trying to figure out what 63 times 63 is and then take the square root of it. It works every single time. Okay? Does that make sense? Now here's a question. I want everybody to think. I know it's Friday. I know it's hot already. Okay? But everybody think, don't say anything out loud. Let everybody think. If I come back to my answer right here, and I reduce this 5 and this 5. You're supposed to be thinking. How many people say, yes, I can cross those out? How many people say absolutely no? Come on, don't be shy. How many people have no, you know what? You didn't vote for anything.
Because I wasn't absolutely no, I was just no.
Alright, why would you say no?
Because you just said you can't reduce. Wait, by the radical bar, you can't.
Exactly right. So when one's on the inside and one's on the outside, I cannot, even just like multiplication, division's the same way. I cannot go through that radical bar. So you're exactly right. Alright, let's try again. Does that make sense though? Anybody confused with any of that? Okay. The square root of 128 over the square root of 5. Now here's a couple different things with this one right here. Can I take 128 divided by 5? No, right? 128, 8 won't be divisible by 5. Could I break 128 down with a perfect square? I don't know, right? So now I'd probably get my calculator out. Somebody start punching that into your calculator. 128 divided by 4. 128 divided by 9. 128 divided by 16. 4 works? 16 works. Let's go bigger then. Okay, 16 is what, Cora?
8.
16 times 8, so it's got to be another bigger one. What's 8 times 16? 64. Do 64. 64 times 2? Yep. Okay. So, again now, if you don't see this, you might have to do this multiple times. But I'm going to try to break this down before I do what we just did over here. Okay? So, the square root of 64 is what? 8. That goes to the outside. And then my square root of 2 stays on the inside because I can't do anything to that. And then on the bottom is my square root of 5. Now try to finish this problem by what we did right over here. Okay? So what am I going to multiply the whole thing by? Remember, Whatever's in the denominator, I'm going to multiply a fraction by itself. So what do we multiply by? Perfect. Now I go straight across the top and straight across the bottom. What do I get across the top? 8 square root of 10, right? Outsides by outsides, insides by inside. What's left on the bottom? 5. Can I reduce 10 and 5? Anna?
Yes.
Can I reduce 10 and 5? No, right? Because of that fraction. Okay, now, if I would have broken this down, I could have done this first part by just taking the square root of 5 times the square root of 5, or over the square root of 5. But then I would have had it done 128 times 5. If I don't have a calculator, that could be a challenge for some of us. Okay? Questions with that? I know this is going to break your heart, but we're not done yet. So we don't have a